Hello, scholars. Welcome back. Professor Henkle here. Today's topic is primary productivity. This is the base of the food web in the oceans. In this world, all life needs to consume energy in one way or another. And the base of the food web are photosynthesizers, organisms that utilize light from the sun, carbon dioxide, and water to produce energy, and a fortunate byproduct of that is oxygen. So here we see marine phytoplankton. They're so magnificent in all these beautiful different shapes and sizes with adaptations to the marine environment that help them to float. Notice the plankton. 3 types of classifications in the ocean: floaters, plankton, swimmers, nekton, and bottom dwellers are benthos. So we have a whole laundry list of items to cover today. Let's get right into it, why don't we? Primary production is the creation of new organic matter from inorganic substances, primarily through this process of photosynthesis, as just discussed. We could define photosynthesis as the utilization of light energy from the sun to produce chemical fuels that is undertaken by plants and algae, which is then eaten by animals, consumers, and then animals eat those animals, and animals eat those animals, and as humans, we can eat animals or plants. We are omnivorous. We have that choice. Such is the cycle of life, but it all starts from primary production. Photosynthesis is not the only way this happens. We've discussed hydrothermal vents, these cracks in the Earth's crust where ocean water filters through, is superheated, picks up all kinds of dissolved solids and metals, and then emits them in these superheated vents called hydrothermal vents, also known as black smokers. Well, there are very distinct populations that these are so deep there's no light down there. And these distinct populations use the process of chemosynthesis, utilizing not sunlight, but hydrogen sulfide to produce sugar and compounds that can then be eaten by other organisms. Wow, that's so cool. I wish we could take a field trip, all get in some submersibles, some submarines, and travel down and have a lecture at a hydrothermal vent, maybe next semester. Byproducts, respiration. So, as organisms use energy, they create carbon dioxide. So we breathe in oxygen, we breathe out carbon dioxide. This breathing out is respiration. It is the release of energy stored in the sugars that carry out the processes of metabolism. So everything respires. Even photosynthesizers still respire. They're breathing in carbon dioxide and they're breathing out oxygen, yes. But through the use, because they also need to power their own systems, through that use, they're also emitting carbon dioxide through this process of respiration. In the oceans, it's this beautiful cycle of photosynthesis, sugars and oxygen, respiration, carbon dioxide and water, back with energy input from the sun to create stability of the chemical environment of the ocean. Production. We're talking about primary productivity, but we could break it down a little bit. Gross production is going to be all of the production that's made. It's kind of like gross revenue. It's all the money a business makes without accounting for any expenses. Respiration is going to be like expenses, right? So you have your gross production minus your respiration, giving you net production or net productivity. And when we look at images of the world and we're looking at oceans, what we're looking at is the net primary productivity. Gross production has new production and regenerated production, but what we're really interested in here is net production. So this points out something really cool. Most primary productivity is along coastlines. And specifically the west coastlines, save up in here around India. Why is that? That mystery we are going to unlock here, but I'll give you a little hint. It's because of coastal upwelling and nutrient availability. Okay, let's continue. So, what photosynthesizes in the oceans? Well, we've got seed-bearing plants, trees, grasses, just like on land, but some live in the ocean, only in coastal environments. They're specifically called mangroves. We've got macro, which means I can see it, seaweeds. We've got micro, which means I can't see it, it's too small. And photosynthetic bacteria. Yes, even bacteria, which is a frontier that we're starting to learn more and more about. Really cool stuff. Let's go through them. Mangrove forest, seed-bearing, only in coastal waters with their roots through the water. Whole ecosystem exists in here because these trees provide protection, security, and food for the animals that live here. Seaweed. Seaweed is awesome. Can be kind of gross when it washes up on this beach that we want to hang out on, but they have those little air sacs that you can squash with your heel and they pop when you do. Anybody? Just me? Check it out next time you see seaweed on the beach and there's these little things that look like little balloons. Just smash it with your heel. It's okay. No seaweed is harmed in the making of this. But there's different types. There's so many types of seaweed. We can think about classifying them as red, brown, or green. We've got rhodophyta, phytophyta, and chlorophyta, different types of macroscopic photosynthetic algae. Then we've got microscopic. Three main categories of organisms here: diatoms, dinoflagellates, and coccolithophores, which we've heard about before. We've heard about all of these before, but in relation to marine sediments, what happens when they accumulate, become silicious or calcareous ooze at the bottom of the ocean, and then lithify into sedimentary rocks. Well, now we're talking about, what about when they're alive? They are primary producers, and the most important primary producers in the ocean. So, diatoms, so cool. They have these shapes that are circular, elongated, and triangular. We find these in cold, coastal, nutrient-rich waters. They have a silica test or shell. We can't see them. Some of them can get up to a millimeter. Maybe you could see them, but we can't really see them. They're microscopic, single-celled algae. So are dinoflagellates, also single-celled microscopic algae. Look at the range of shapes for these things. That is amazing. I cannot believe that the ocean is jam-packed with these in certain places. They don't have a mineralized shell, but they have shells made of cellulose, so they don't really deposit as marine sediments. They do have a flagella, which are these whip-like tails that they can scurry around a little bit. They do float in the ocean, so still considered floaters. And coccolithophores, single-celled algae that have a wide range of sizes from 5 to 100 micrometers. They're really, really small. Look at these small circular discs that are stacked up. This is an electron microscope. These are made of calcium carbonate, carbon from the ocean that they put into their shells. Then when they die and they accumulate, they settle at the bottom of the ocean as calcareous ooze. That calcareous ooze becomes chalk. The white chalk cliffs of Dover? Yeah, so cool. The Earth is all connected in various ways. What we're learning about more and more are picoplankton, single-celled bacteria that are really important for oxygenating our atmosphere. So not a ton to say on them, but they're very tiny, and now we're learning very, very important. So what influences primary productivity? Is it temperature? No, because the temperature in the oceans is pretty stable. There's the mixed layer, and then the thermocline, and then shum, leading to density differences, salinity differences. No, it's light and nutrients, because primary production is photosynthesizing plants and algae in the ocean. So they need light, so they've got to be close to the surface. They also need nutrients, the most important nitrates, but also phosphates in order to reproduce. So light and nutrients combine to create areas of high primary productivity. Primary productivity, sunlight and nutrients combine for primary productivity. These are the two most important things that we have. Light happens in the euphotic zone. The rate of photosynthesis decreases as light decreases with depth. At some point, there's the compensation depth because, as mentioned, these organisms respire. The respiration rate is constant down. So when respiration equals photosynthesis, there's no more net productivity. This is the compensation depth. Nutrients. The main nutrients are going to be nitrates, nitrite, and ammonium phosphates. Now, we also need silica for shells of diatoms, calcium carbonate for shells of coccolithophores. But without nutrients, we're not getting these primary producers reproducing to the levels that we need to create the environments and support the base of these food webs. How do we get the nutrients? We mentioned it earlier, right? We get the nutrients through the process of upwelling. When organisms die, they settle to the bottom of the ocean. Organic material decomposes by decomposers. But in certain areas, there's upwelling along coasts and areas of divergence in the ocean. So if we look at a world map, we can see coastal upwelling along the west coast of continents are the highest net productivity areas in the entire world. They're not the only ones, but they are definitely the highest. Patterns emerge globally, and we can talk about these patterns through time and space. Space is going to be by latitude, geographic. Time is going to be seasonal. Now, what coincides with seasonality? The availability of light. So if we think about light availability and latitude, which changes where there are upwelling and changes also the availability of light, then we can look at patterns. Primary productivity in tropical areas, relatively constant all year. For northern hemisphere, primary productivity in poles has a boom in spring, summer when the light comes out. And in tropical areas, or in temperate areas, there's an increase in spring and in autumn bloom. So patterns in primary productivity, this shows it by season and by geography. You put these two together, varying amounts of net primary productivity. Okay, so let's review. What does primary productivity need? Light and nutrients. And what affects the availability of those? Seasons and geography. Okay, really good. So let's look at each one of these. Temperate, this is the green one. The most net primary productivity happens in temperate environments because there's a spring bloom and an autumnal bloom. There's a pretty steady low rate of productivity with these two blooms all year round. In tropical, basically the temperatures stay the same. You have your mixed layer and your thermocline, which prevents nutrient availability. Now there are some from equatorial divergence, which creates upwelling, but that is steady. Doesn't vary by season, doesn't vary by light. So you get a low rate of primary productivity because of low rates of nutrient availability. And in the poles, you have a spring bloom, basically dark 6 months, light 6 months. When the sun comes out, there's tons of nutrient availability. It's light deficient in poles. Tons of nutrients, so when the sun comes out, boom. Huge net primary productivity boom. What we see is that zooplankton, blooms, the animals that eat the phytoplankton follow phytoplankton blooms. We'll talk about this in animals of the benthic, because they're benthic animals. So, is primary productivity always a good thing? It is a necessary thing. We do want it, absolutely. But primary productivity in excess can cause harm. When dinoflagellates are overabundant, they can create what's called, or diatoms or coccolithophores, they create a harmful algal bloom. This is known as an HAB. HABs can turn red, and they come from an explosion in algae populations that change the color of the water. Here's a red tide near the Scripps Institution of Oceanography, great place to study oceanography and also red tides. These red tides can get into the organisms that live in that environment, bioaccumulation of toxins, which are then eaten by people, biomagnification, and can cause some pretty bad stuff. Paralytic shellfish poisoning or amnesic shellfish poisoning. Got to be careful about the shellfish you're eating. That's why some people are so weary about it, because it can have harmful effects if absorbing too many toxins. Well, this concept of harmful algal blooms, which are natural, can be exacerbated by human impact through this process of eutrophication. It is the artificial enrichment of waters by previously scarce nutrients. Here we can see algae cleanup in China before the 2008 Olympics. This was a bad time for algae to explode, where all of the rowers were about to have their competitions. But these things happen. Where do the nutrients come from? Sewage, fertilizer, and animal waste. Where are those produced? Cities and farms. These are human impacts that are affecting marine environments. Lots of effects, but this is one of them. These eutrophication creates hypoxic areas, which means low oxygen, creating dead zones. So it happens like this. Lots of nutrients put into the water. The algae has an overabundance, an explosion. The algae dies and sinks to the bottom. The decomposers decompose all of that algae, use all the oxygen, denuding those waters of the life-giving oxygen that all of these marine organisms need. They either leave or they die, creating a dead zone. This is bad news. We see that dead zones happen all over the world. They're normal, but there's also not in this frequency and distribution. Right now there's over 500 worldwide. They're doubling every single decade since the 1960s. They can be caused by unstratified water columns and cause a tremendous amount of harm, like in the Gulf of Mexico. So the Mississippi River has a huge watershed, the amount of land that it drains, and it all drains into the Gulf of Mexico. So all of the runoff and nutrients from all of the farms and all of the sewage in this huge Mississippi River watershed delivers to the Gulf of Mexico. And this happens every single year. It's not, is there going to be a dead zone in the Gulf of Mexico? It's, how bad are the effects of this year's dead zone going to be in the Gulf of Mexico? It's the second largest in the world. As it comes out, you can see there's areas of zero dissolved oxygen. So when this happens, it's really hard for anything to survive. So what do we do? There's a lot that we can do. There's always a positive. It's like, oh no, doom and gloom, we're destroying the world. It's over. Let's just bury our heads underneath a pillow and never come out again. No. There's things we can do. I like to stay positive about the world in which we live in and will live in. So we can control the amount of nutrient runoff. Preserve wetlands. Wetlands are natural water filters that can pull some of the contaminants, the excess nutrients, out of these waterways. Plant buffer strips of trees and grasses between farms and streams that'll help keep some of these excess nutrients out. Improve crop rotation and other conventional agricultural practices. And then enforce existing clean water regulations. It comes down to human practice and environmental policy for us to really move forward into the future in a way that limits the damage that's being done. We can do it. You can do it, I can do it, I know we can. Even though we don't live in these areas, that's fine. We can still support these kind of movements. How? Reducing our own pollution, voting for politicians that have an environmental agenda, being active in these issues, learning about them, talking about them, all the things that we're doing. So good job. Keep it up. You're doing great. Primary productivity is vastly important because this is the base of the food web in the oceans. Phytoplankton use sunlight, carbon, water to produce energy that's then eaten by animals. And this is wildly important. It's the base of most marine food webs. It varies. Okay, quiz. Primary productivity needs light and nutrients and varies by geography and season. So good. It is critical for healthy marine environments to not upset the balance through the process of eutrophication, but to let nature run its course and not to throw off that delicate marine ecosystem. And I say delicate because it is. It can take a lot, the oceans, but we can't just keep dumping all of our trash and waste and throwing it in the ocean and saying the ocean can take it. No, the ocean can't. It's an early warning system for the health of our Earth, and we really can look towards the ocean to see what the thermometer of health of our entire planet is. So thank you very much. That's really awesome. A lot of good stuff on primary productivity, the basis of the food web, the photosynthesizers, chemosynthesizers too, of the marine environment that will springboard us into our conversations about animals that live both in the open ocean, pelagic, and on the ocean floor, benthic environments. Thank you, and have a nice day.